Hi guys, sound check, just in case. And as I can see, there are not, well, there are fewer of us, so I believe we should wait a couple of minutes before start. By the way, as I know you have an English exam during this week, does it interfere with your lectures and seminars?
Can you repeat, please?
Oh, I've got an email from the office, and they told me that you have some kind of English exam during this week. I just want to know, does it interfere with the lectures and seminars or not?
Well, actually, for example, first and second group, we have quarantine now, so this exam is cancelled.
Oh, I see.
So
So you're well, you're kind of lucky and at the same time not. I see. That's a pity. I believe that's inconvenient. Okay. I think we should start. I just start from...
May I ask a question?
Yep.
So as far as I know, we're supposed to have two control works, right? Like the first
No,
one
just
is
one. Just one test. One test and one exam. The test will be written test and the exam will be oral.
Yeah. So when are we going to have the written test? Because it isn't scheduled at all, and like it is a little bit unclear.
Okay. Yeah. Well, I believe during this week, since we have like a week and a half till till the end of this module. So I don't know. Probably during the next week we will got this test.
And will you send us like a demo variant or something like that?
No, there is no demo variant for the test. Well, if you want to prepare yourself for the test, you should know how to solve all the problems from your homework. I mean, the problems will be more or less exactly the same. So I just want to know how well, how can you prove the problems that we already discussed? So there will be nothing new during the test. So this is the main rule. I just want to know, well, how did we teach you and how can you solve the problems we taught you? That's it.
Okay, thank you.
No problem. Yeah, well, I thought that you have this exam during this week, so I didn't plan. Well, actually, my plan was June 12th, but unfortunately, June 12th is the holiday. So I have to find a day during the next week. So I'll send you an email with the information, and don't worry. Okay, I believe we should start. There are not so many of us, but that's not a big deal. I believe if you came here, it should be interesting. Okay, so let me recall what we're doing. Currently, we deal with polynomials with several variables. What does it mean? We fix a field, then we consider the polynomial ring in several variables, and we fix a lexicographical order on the monomials. So first we fix some order on the variables, for example, we choose this one, and then we specify the corresponding lexicographical order for the monomials. And now we have a reduction process which generalizes the Euclidean division algorithm. Well, so if we have a subset of polynomials, non-zero polynomials, and some other polynomial f, we can reduce this polynomial with respect to the set G to a polynomial which is called remainder. And well, in general, there is an issue with this process. If we do that, it may happen that the same polynomial may have different remainders. Just in case, let me recall what does it mean that we have a remainder. Well, we have a process of elementary reduction, so we can reduce a monomial inside F with respect to a polynomial from G capital. This is an elementary reduction. And then we can repeat this process. And we know that after finitely many steps, this process terminates, and we will get a polynomial, let's say R1, and there is no possible reduction of R1 with respect to G capital. And if we cannot reduce such a polynomial, it's called a remainder. But there are many different ways to reduce your polynomial with respect to the set G. For example, you may find a completely different path and at the end, you will get a completely different remainder. So it may happen that these two are different. And there is a definition of a Grabner basis. We say that the set G is a Grabner basis. So I already, well, the definition has already been given. So I just want to recall the definition. So G is called a Grabner basis if for every F, all its remainders are the same. So if every polynomial has unique remainder, So as you can see, a Grabner basis is a very convenient set to deal with. However, there is one problem. How do we check if something is a Grabner basis? So how do you check that this property holds? Because, well, how do you go through all the polynomials and how do you find all the possible remainders and compare them? It's inconvenient. So instead, we want to have a better solution for this problem. And there is a criterion which is called a Buchberger criterion. And my goal today is to formulate this criterion. And I want to provide you with several algorithms that follow from this criterion. And during the next lecture, I will prove the criterion. So, but before I can formulate the criterion, I need one auxiliary definition. So the definition of an S polynomial. Well, suppose we're given two polynomials, G1 and G2. and we assume that some order is fixed. Let's say we have some lexicographical order to be fixed. Now, we know, since we have the order, we can find the leading term in each polynomial. So G1 can be represented as C1 M1 plus G1 prime, and G2 can be presented in the form C2 M2 plus G2 prime. And this is the leading term of G1, and this is the leading term of G2. Here, C1 and C2 are coefficients, and M1 and M2 are monomials in the variables x1, xn. Okay, now I want to produce a new polynomial given these two. And this new polynomial will be called S polynomial of G1 and G2. Here is the way how you do that. First of all, you need to compute the least common multiple of M1 and M2. So the least common multiple of M1 and M2. Let's say it's M. Since it's the least common multiple of M1 and M2, it can be presented as M1 times T1, where T1 is some monomial. And it also can be presented as M2 times T2, where T2 is also a monomial. So T1 and T2 are monomials. So now we're ready to give the definition of the S polynomial. So let me briefly discuss what I'm going to do. So I want to multiply this polynomial by a monomial with coefficient and this polynomial by a monomial with coefficient in such a way that the leading terms become the same. And then I subtract one polynomial from the other and cancel the leading term. So this is what I'm going to do. So I need to multiply G1 by C2 and T1. So I'm going to produce what is called S polynomial of G1 and G2. What I'm doing is this. I take G1 and I multiply it by T1 and C2. I take G2 and I multiply it by T2 and C1 and subtract one from the other one. So let's see what we will get here if we substitute the expressions for these polynomials from the above. So here we have C2 T1 times C1 M1 plus G1 prime minus C1 T2 times C2 M2 plus G2 prime. Well, as you can see, well, this part multiplied by this coefficient and this part multiplied by this coefficient, they are the same because T1 times M1 is equal to T2 times M2. So they are cancelled. And so this will be the leading term of the product. And this blue part will be the leading term of this product. And because of this subtraction, we cancel these leading terms and we will get this polynomial. And here we have just the tails of these guys, G1 and G2. And as you can see, well, in general, it may happen that, well, here, so in this expression, we have no terms divisible by the leading term of G1 prime, and here we have no terms divisible by the leading term of G2 prime. Okay, so this is the definition of S polynomial. So this is the definition, this equality is the definition. And this computation just shows you that after these, when I expand the parentheses, I cancel the leading terms of the summons. This is what happens here. So in general, it's unclear, is it possible or not to reduce this polynomial with respect to G1 or G2 because it doesn't contain the leading terms of these summons. Okay, so this is S, so let me repeat the name. This is S polynomial. Polynomial of G1 and G2. So let me give you an example.
Wait, can I ask a question?
Yeah,
Like,
no problem.
why is it so important?
As polynomial?
Yeah, like what's
Okay, yeah. The reason why it's special, well, you'll see in a second that in the criterion how to check that if a set is a Grabner basis or not, it's enough to deal with S polynomials of the elements of this set. So somehow we reduce the problem of checking a remainder of all the polynomials to the problem of checking the remainders of S polynomials. You'll see in a minute.
I see. Yeah.
So the reason why it's important, because it's a crucial component of the criterion I'm going to present you. So an example, if we take, let's say, the theorem of polynomials with rational coefficients, and I want to fix the lexicographical order with respect to this ordering of the variables, then the first polynomial G1 let be something like this, xy minus 1, and the second one is yz minus 1. So this is the leading term. The leading coefficient is 1. So the least common multiple of the leading term of the leading monomials is xyz. Well, as you can see, z becomes t1 and x becomes t2, according to the definition above. So now what we're doing, we multiply g1 by z, we multiply g2 by x, we subtract one from the other one, and what do we have? Well, we have xy minus 1 times z minus x times yz minus 1, and the result will be x minus z. So as you can see, the leading term of this summand and the leading term of this summand is cancelled, and we have something very small here. And this polynomial, as you can see, is not reducible with respect to these two ones. Okay, so this is an example of an S polynomial. So now, the reason why I need S polynomials is the following criterion. Let me formulate the criterion itself. So the claim, oops, the wrong color. The Buchberger criterion. Okay, so let me formulate the criterion. First of all, we're given a field and the polynomial ring in n variables, and we fix a lexicographical order. So this is what we are given. Now, we also have a set of non-zero polynomials. Now, the following are equivalent. The condition number 1, G is a Grabner basis. The condition number 2, for every polynomials G1 and G2 in G, their S polynomial is reducible to 0 with respect to G. And here, when I'm saying is reducible to 0, I mean there is at least one possible way to reduce it to 0. There exists. Well, actually, well, let me formulate it more accurate, in a more accurate way. The claim number 2, the item number 2 says that for every pair of polynomials, their G1 and G2, their S polynomial is reducible to 0. And here I assume for every possible reduction, for every reduction. And the claim number 3, the item number 3, says that for every 2 polynomials, G1 and G2 from G, their S polynomial is reducible to 0 with respect to G. And here, I mean, there exists at least one reduction of this S polynomial to 0. There exists a reduction. So these three statements are equivalent. So let me compare these two statements first of all. So I mean, if you find at least one way to reduce each S polynomial to 0, then it automatically means that the set is Grabner basis. But if the set is Grabner basis, the remainder is uniquely defined. So it means that each S polynomial is reducible to 0 with respect to any reduction. So there is no difference between these two options. But if you want to check if the criterion holds, you do it like this. You take a set G. For every pair of polynomials, you produce S polynomial. You try to reduce it to 0. You can use any reduction you wish, like choose randomly, or like any preferable way to reduce it to 0. If you can reduce every S polynomial to 0, then this is a Grabner basis. And it doesn't matter which reduction you choose. And if at least one reduction is not 0, so if at least for one pair, G1 and G2, you can find a reduction to a non-zero remainder, then the set is not a Grabner basis. So this is how you use this criterion. So now it leads to an algorithm how to check if a set is a Grabner basis. You just strictly apply all these rules. For example, if we go up to the previous, to this case, if you consider the set consisting of G1 and G2, this is their S polynomial, and as you can see, this S polynomial is not reducible with respect to G1 and G2 because neither term is divisible by the leading terms of G1 and G2. So this is already a non-zero reduction of an S polynomial with respect to G1 and G2. So the set consisting of G1 and G2 is not a Grabner basis by this criterion. From the other hand, yep.
Sorry, can I ask a question?
Yep.
It's a little bit dull. So what is a Grabner basis?
Oh, okay, let me recall this. So the definition was here. So the set G is a Grabner basis if every polynomial has a unique remainder. So this is the definition of the Grabner basis.
Okay,
so it means
thank
that,
you.
Yeah. So it means that for every polynomial, all remainders are the same. So as you can see, the item number 1 assumes that you have to go through all the polynomials in this ring, and you need to compute all possible remainders, compare them, and check if they are the same or not. But instead of doing that, it's actually quite hard to do because how can you go through all the polynomials? It's well, you cannot do this algorithmically. But the claim number 3 says that, well, instead of doing that, simply you need to compute S polynomial for each pair, and then if you can reduce all S polynomials to 0, it's a Grabner basis, and if you cannot reduce at least one to 0, then it's not a Grabner basis. Okay. I want to make another remark regarding to this criterion, but yeah, but just in case, are there any other questions about the claim? Should I clarify something here?
Yeah, could you repeat it again, please? If the second one said that for any G1, G2, there should be a way, and the third one says that there is exist.
No, in both cases, you require to check all the pairs here. Here for every G1 and G2, and here for every G1 and G2. The second part is different. This statement says, for every G1 and G2, every reduction of S polynomial gives you 0. I mean, every reduction to a remainder. The third part says for every G1 and G2, at least one reduction gives you 0.
Okay.
So, and this is what is easy to check, because, well, you don't need to go through all the possible reductions. You just need to find at least one reduction to 0. And if you find at least one reduction to a non-zero remainder, then, well, it contradicts to the second part, so it's not a Grabner basis. So this is why I separated these two claims, because this one is easy to check if G is a Grabner basis, and this one is easy to check if you want to show that G is not a Grabner basis. Okay, now there is another remark. If your set G consists of one polynomial only, then it's always a Grabner basis. Why? Well, because the set of S polynomials is empty. I mean, you can produce S polynomial of G with itself, but by definition, it will be 0. So it's not interesting. So that's so it's trivial. Well, it's trivial. Well, it's really simple. How to well, using this criteria, it's really simple to check if a set consisting of one polynomial is a Grabner basis. Okay, but it's
could you remind the definition of Grabner basis again?
Okay, it means that the remainder of every polynomial with respect to G is the same. So if you take any polynomial and you take two different reductions, they always lead to exactly the same remainder. So the division with
any polynomial from the same field. Yeah.
Yeah. Okay. Yeah. I mean, we fix this ring, and we deal with polynomials inside this ring. So we fixed a field, and we fixed the set of variables f and x1, xn. They are fixed, and we also fixed a lexicographical ordering. So all these things are fixed.
But
and then we take every polynomial here.
I don't see any correspondence with like a normal basis and this basis. Like,
oh, why is it called basis?
Yeah.
Okay. Well, actually, there is it's a tradition. Actually, during the Russian course in algebra, we use term Grabner system instead of Grabner basis. But the Grabner basis is the term used for ideals in this ring. You'll see in a minute why I use this term basis. I'll give you the corresponding remark in an appropriate place. But should I continue with the description of the Grabner basis with the definition, or is it clear?
It's clear.
Okay, no problem. So yeah, and now there is one important remark. Well, another claim. Yeah, I don't want to prove the criterion today. I want to postpone the proof till the next lecture. Well, it's not very easy, but I just want to derive some corollaries from the criterion. And I want to discuss some important things you should know about the Grabner basis and how to deal with them. So the next claim, also without proof currently, is the following. If you have two polynomials, G1 and G2, here, and of course, I assume I have some way to compute their leading terms, and suppose, well, I just want to repeat this notation because I want to have a notation for their leading terms. Well, yeah, and these are the leading terms. Then, if M1 and M2 are co-prime, so GCD of M1 and M2 is equal to 1, then S polynomial of G1 and G2 always reduces to 0 with respect to G1 and G2. So this is an interesting fact, which ensures that in some situations, the S polynomial will automatically goes to 0. This claim allowed us to reduce the amount of pairs to check. So if you, for example, if you have something like this in the polynomial ring x, y, z with this order on the variables, if you consider two polynomials, g1, x squared y minus z, and g2, z squared minus 1, then what are the leading terms here? Well, the leading term here is x squared y, and the leading term here is z squared. And as you can see, they are co-prime. They do not have a common multiple. So since they're co-prime, so their GCD is 1, then the set G1, G2 is a Grabner basis with respect to this order. However, if you switch the order, for example, if you take z higher than y and higher than x, then the leading terms will be these ones. And they are not co-prime, and you have to use the Buchberger criterion in order to check if the set is a Grabner basis or not. And it may happen that a set of polynomials is a Grabner basis for one specific order, and it's not a Grabner basis for another order. So yeah, it may happen. But here it was an example how to check if some S polynomial is reduced to 0 automatically. And this is the case when it happens. This is one of the cases when it happens. Okay, now I want to clarify the term, well, the word basis in the term. So let me show you why we call it basis. Well, actually, we want to deal with ideals in the polynomial ring, f of x1, xn. We want to understand how the ideals here look like. First of all, we can produce what's called a finitely generated ideal. Let's take polynomials g1, gk from here. Let's say the definition. Then I want to define the subset, which is denoted like this, g1, gk in parentheses. And by definition, this is the set of all polynomials of the form, where hi are all possible polynomials in n variables from this ring. So strictly, well, simply speaking, what is this? Well, you just take all possible combinations of g1 and gk with coefficients being polynomials. And what you can check that this set is an ideal in f of x1, xn. Well, indeed, it's an abelian subgroup, and it's closed under multiplication by any polynomial. So this is just by definition. It's a straightforward computation. Well, in particular, well, a different notation for the same ideal. So if you have a finite set, G consisting of polynomial G1, Gk, I can also denote this set by G capital in parentheses. So this is exactly the same thing. I just want to clarify that that's a different way how to denote it. So this is an example of ideals in the polynomial ring. And it may happen that, well, in general, well, if you have a polynomial ring in one variable, you know that every ideal is generated by one polynomial in this sense. Well, when you have several variables, it's not true that every ideal is generated by one polynomial. But what is true that every ideal can be presented in this form. And this is what is called the Hilbert basis theorem. Let me formulate the claim. The claim, the Hilbert basis theorem. It says that every ideal in the polynomial ring where F is a field, there exists G1, Gk such that I is equal to the ideal generated by G1, Gk. We will call, so if this happens, if I is equal to this ideal, we will say that I is generated by G1 and Gk. So if you want to specify an ideal in the polynomial ring in several variables, you need to specify finitely many polynomials. Okay. Now, we want to deal with the ideals in an efficient manner. What does it mean exactly? Well, for example, we want to check if something belongs to the ideal or not. Well, how to solve this problem? Well, in some way. Well, in order to do that, we need to use Grabner basis. And how do we use the Grabner basis? Here is an idea. Well, suppose we have an idea. Well, let's start from the beginning. So, well, we have this. F is a field, and we're given finitely many polynomials. And these polynomials, they define an ideal I. I just want to denote it by I. And now, what we want to do is this. We want to fix a lexicographical order. So when we are given an ideal, we do not have any specific order on the monomials. So we need to introduce such an order. So we fix a lexicographical order. Since we fixed the order, we have the notion of a Grabner basis. So now what we want, so let me write it like this. We want to find a finite set G consisting of polynomials G1 prime, Gm prime, with the following properties. The property number one, the ideal I is generated by the set G. So these new polynomials generate exactly the same ideal. And the property number two, G is a Grabner basis. So now it makes sense because we have already fixed the order. So if we have an order, then we have the reduction process, and the notion of a Grabner basis is well defined. So simply speaking, we want to change the generators of the ideal I in such a way that the new generators form a Grabner basis. And if we can do that, we can solve all possible problems related to the ideals algorithmically. So now I want to split this explanation in two parts. The part number one, I want to explain how to find such a set of generators G. So yeah, and the reason why we call G a Grabner basis is actually because this set G generates the ideal. So this is the context where the Grabner basis appeared the first time. So people just wanted to deal with ideals, so they wanted to find some good generators, and they called these good generators by a basis somehow. It's not a basis in the sense of linear algebra or any other sense, but it's just a good set of generators for I. So yeah, and the first part I want to explain is how to find this good set of generators. This will be the first part. And the second part, I want to discuss the problems that we can solve if an ideal I is given by, well, is generated by a Grabner basis. So now, before going any further, are there any questions regarding what I have explained? Okay, so now there is what is called a Buchberger algorithm. Buchberger algorithm. So the context, so what do we have? What we're given, we have a field. Oh, I'm sorry, I'm writing something completely wrong. We have a field, we have this polynomial ring over this field, and we have a fixed lexicographical order. So we need to specify all these things before even trying to formulate the Buchberger algorithm. So we must be given all this stuff. Now, as an input, this algorithm takes a set, let's say F, consisting of polynomials F1, Fm. This is just a subset here. And as an output, it must produce a set G, actually containing F, such that it has three properties. G is finite. The second property, G is a Grabner basis. And the third property, G generates the same ideal as the set F. Oh, I'm sorry, F is already taken as a letter for fields. Let's say F prime. I'm sorry for that, I didn't notice. So I just wanted to denote a set of polynomials by a capital letter. I didn't notice that it's already taken. So yeah, so this is so the algorithm does exactly what I have announced before. So I just want to extend this set by a bigger set, which becomes a Grabner basis generating the same ideal. And here is what algorithm should do. So the algorithm itself. Well, so what do we have? We have this set F prime. First of all, we take all possible pairs. I'm sorry, not G, but F. And so we need to go through all possible pairs of this set F prime. And then we produce for each pair the corresponding S polynomial. Then we reduce each S polynomial with respect to F prime to a remainder. And then, well, if all the remainders are 0, then the set F prime is already a Grabner basis, and this is your G. So if all Rij are 0, then F prime, well, then G is F prime, and this is the answer. If not, then we take we add all the non-zero remainders to F prime, and repeat the procedure. So this is the algorithm. So we produce all possible S polynomials. If then we reduce them, and if we have at least one non-zero remainder, we add them all to the set F prime, and then we repeat the same procedure for the new set. We produce all the possible pairs, we compute S polynomials, we reduce them, and if we can find at least one non-zero remainder, then we add them to the previous set, and so on and so on. So the process, while we're doing this process, we will produce a sequence of sets, like f prime will be the first set, like f1, let's say. Then we will produce on the second step f2, which will be strictly larger. Then we will produce f3, which will be strictly larger, and so on. And what is important, this process terminates. We will always stop at some point. What does it mean? It means when we get this set Fn, then and apply this this algorithm to this set Fn, we will not get non-zero remainders in this case. So by definition, Fn will become a Grabner basis. So I'm not proving the claim why the process terminates, but if the process terminates, the set at the end will be a Grabner basis, just by definition, by the Buchberger criterion. So Buchberger actually invented this algorithm, and in order to prove that this algorithm works, he proved his famous criterion.
Sorry, can I ask a question?
Yep.
So fi and fj is a polynomials, yes?
Yes, they are polynomials. Yeah.
Well, then S fi fj is also a polynomial.
Yep, it's a polynomial.
So, like, what is the difference?
Difference between what and what?
Like between pair fi and fj and S fi fj.
Well, here you have two polynomials, and here you produce a polynomial using these two ones.
Is it like just multiply two polynomials?
Oh, how do you produce? So what is the definition for this polynomial?
Yes.
Okay, the definition of this polynomial was here. It's an S polynomial. This is the rule.
Oh, this one. Okay.
Yeah. That's exactly this specific polynomial. So for each pair, you produce this specific polynomial using these specific rules. So this is why I use this term S polynomial. So let me clarify this part here. So this is nothing but S polynomial.
Right. Okay. Thank you.
Yeah. Okay, no problem. So it's not just a random polynomial. You just produce this specific polynomial using these specific rules. Okay. Now, yeah, we will try to compute Grabner basis during the seminar sessions, but now I want to discuss what kind of problems we can solve using Grabner basis. So, okay. Well, as you remember, when we dealt with the ring of polynomials in one variable, I introduced you the notion of a remainder ring. So if you know what is a quotient ring with respect to an ideal, well, that was just a different approach to the quotient rings without giving you the exact procedure or exact definition of a quotient ring. Now I want to define a quotient ring in the case of polynomials in several variables. And I will also call it the remainder ring. So the ring of remainders in several variables. Well, okay, so I want to make one general remark. Well, there are two ways of defining this ring. The way number one requires the notion of a quotient group and a quotient ring. It's a very complicated definition, and it's very hard to get used to this definition. But what is good about this general definition that you don't need to specify generators of your ideal if you want to produce such a ring. There is some general process of producing a new ring when you're given a ring and an ideal. what I'm going to do, I'm going to give you some kind of a coordinate definition of a quotient ring, and I will call it a remainder ring. The biggest disadvantage of this definition is that this definition will depend on the choice of generators for an ideal. And I will discuss how it depends on this choice. But that will not be very important. Okay, so now, what is the procedure? As usual, we're given a field and the polynomial ring in several variables. And I want to specify the order at the beginning. So everything is given. Now, I want to get an ideal where G1, Gk are just arbitrary polynomials here. And now, since I have an order, I can compute the Grabner basis for this ideal. Okay, so the latter also means that I is generated by G0. Now I can give you the definition of a quotient ring, and this definition will depend on the choice of this Grabner basis. So
is the Grabner basis unique or?
No, it's not unique.
Okay.
It's not unique. The Grabner basis is not unique. That's an issue, actually. There is some canonical Grabner basis for each specific order, but in general, an arbitrary Grabner, well, there are a lot of different Grabner bases. Okay. Now, for example, there is an infinite Grabner basis consisting of all the polynomials from the ideal I. It's not an interesting one. You cannot use it efficiently, but it's a Grabner basis nevertheless. So now I want to define something which will be denoted by these symbols. I take the polynomial rings, I take the quotient, and I write here G0 in parentheses. So this will be the ring of remainders with respect to G0.
But didn't we already have this notation?
Yeah, we already have this notation, but in case of polynomials in one variable, it will be coherent with this notation. I mean, for several variables, I didn't define you the notion of a quotient ring in general, so it doesn't matter. It's not an issue. So now, how do I define this thing? Well, I define it as the set of all remainders with respect to G0. So this is, so if I want to define a ring, I need to specify a set and two operations, addition and multiplication. Currently, I have specified the set. So as the set, it's just the set of all remainders with respect to G0. So you just take all the monomials not divisible by the leading terms of elements of G0 and take their linear combinations. So this is just linear combinations of monomials not reducible by G0. Okay, so now I want to provide you with two operations, an addition and multiplication. Well, the case of addition is simple. If you take two remainders here, and if you add them together, then the sum is also a remainder. Indeed, why is this true? Well, how do you check if something is a remainder or not? Well, a polynomial is a remainder if and only if every monomial of this polynomial is not divisible by the leading terms of G0. Well, if all monomials here are not divisible by the leading terms of G0, and all monomials here are not divisible by the leading terms of G0, then their sum has at most the union of the monomials from F and F prime. So all the monomials here are definitely not divisible by G0, by the leading terms of G0. So the usual sum of polynomials is a well-defined operation here. So now I want to specify the multiplication. Well, if you take these two polynomials, F and F, well, remainders F and F prime, you can multiply them using the usual product of polynomials. Product. But after this multiplication, the result need not be remainder. Now, you reduce the result with respect to G0 and you get a remainder. And by definition, you say that F multiplied by F prime is equal to R. So this is the definition of the multiplication. So you multiply two polynomials and then you compute the remainder. So this is the definition of the multiplication. Well, I don't want to check this, but one can show that this indeed defines a commutative ring with an identity. That this thing is a ring, actually commutative. Well, I just want you to believe me. Well, because, well, there is actually a very simple proof, but it requires using a notion of a quotient ring. I just don't want to go into these details. But what is important is to know how the set looks like and how the operation works. Okay, so again, this is the set, and these are two operations. The addition is simple, and multiplication is a bit trickier. So you just multiply two polynomials and compute the remainder. So this works exactly in the same way as it works in case of polynomials in one variable. So this definition is consistent with the case of one variable we already discussed. So this is just a generalization of this construction to the case of several variables. But just in case, are there any questions regarding this procedure? Should I clarify any details? Okay, so now I want to make several remarks. Oh, yeah, and I should go up, I believe. So as you can see, this definition depends on the choice of a Grabner basis. So I want to discuss well, this dependence. So a remark number one. So, well, here is our set with the fixed order, lexicographical order. So if we have an ideal I, we may find two different Grabner bases. We may find a Grabner basis G1, let's say G2, and a Grabner basis G1. These are two different Grabner bases for I. And then we may produce the corresponding ring using G1 and G2. So we may produce, yeah. So what will change? Well, actually, if so, yeah. Let me underline. So here we have a fixed order. So both Grabner bases are computed for exactly the same order. In this case, well, again, I'm claiming this without proof. If the order is exactly the same, then for every polynomial, we have this property. You can reduce a polynomial with respect to G1, and you will get R1. And you can reduce your polynomial with respect to G2, and you will get R2, the two remainders. What will happen the equality will always hold. So if you change a Grabner basis G1 to a different Grabner basis G2, the set, which is this one, the set of all remainders will be exactly the same as the set of all remainders with respect to G2. So the sets will be the same. And actually, one can show that this equality of sets defines an isomorphism of rings. So, I mean, if you take a remainder here, it corresponds to exactly the same remainder here because the sets are the same. And this equality is an isomorphism. What does it mean exactly? It means that the multiplication defined with respect to G1 coincides with multiplication defined with respect to G2. Indeed, well, if you take f and f prime, how do you compute their product? You compute the usual product of polynomials, and then you reduce it with respect to G1. And this will be their product in the left ring. But how do you compute their product in the right ring? You multiply these polynomials using the usual polynomial product and reduce it with respect to G2, and you'll get R2. But because of the previous remark, these remainders must always be the same. So the product in the left and the right hand side is exactly the same. So if you change a Grabner basis with another one, you will not change the ring at all. Nothing will change. So in this sense, this ring doesn't depend on the choice of Grabner basis when your order is fixed. Now, what happens if we change the order? So what we can do, we can take two different orders, lexicographical order 1 and a lexicographical order 2. For example, for the first one, we say that x1 is greater than x2, etc., etc. And for the second one, we have the opposite order on the variables, like xn is greater than xn minus 1, and so on. So for the ideal I, we may compute its Grabner basis with respect to lexicographical order 1, and we may compute its Grabner basis with respect to lexicographical order 2. So this is a Grabner basis with respect to lex 1, and this is a Grabner basis with respect to lex 2. Well, in this case, it's not true that the set of remainders will be the same. We will get two different sets of remainders. So we will get the set of remainders for G1, and we will get the set of remainders for G2. And these are two different rings. But these two rings are actually isomorphic. So one can find an isomorphism between them. So they will always be isomorphic. So we can find an isomorphism between them. And this isomorphism works like this. If you have a remainder with respect to G1, just compute its remainder with respect to G2. And you can map each remainder f to on the left-hand side to a remainder with respect to G2 on the right-hand side. This will be the map giving you an isomorphism. A reverse map is given by exactly the same procedure, but here, if you're given a polynomial g, you just take its remainder with respect to G1, and this gives you the map in the opposite direction. And one can show that these two maps are inverse to each other. They respect addition and multiplication, so these maps are mutually inverse bijections, and they are homomorphisms, so they give you an isomorphism. So you can prove, so one can prove all these claims, but I just don't want to do that here. So what is more important is just to know the exact formula for the isomorphism, and to know that these two rings will always be isomorphic. So in some sense, if you want to deal with this ring of remainders, it doesn't matter which order you choose and which Grabner basis you choose. Okay, so now let me explain what kind of problems we can solve using Grabner basis of ideals. I want to focus on two specific problems. Problem number one. Well, suppose we have this polynomial ring, F is a field as always. We have an ideal, and we have a polynomial. Now we want to check if a polynomial belongs to the ideal. But yeah, we want to define the ideal by a finite set of polynomials. So we assume that I is given by a finite set, and we're also given a polynomial f, and we want to check if f belongs to I. How can we answer to this question? So, and here is the way how to do that. Well, first of all, we need to fix a lexicographical order. And now we have the notion of a Grabner basis for the ideal I. The second step, we compute a Grabner basis. A Grabner basis for the ideal I. And here we use the Buchberger algorithm for doing that. Then what we're doing is this. We take our polynomial f and compute its remainder with respect to the Grabner basis. Let's say it will be R. Then there are two options. The remainder is either 0 or not. Well, if the remainder is 0, then f belongs to the ideal, and if the remainder is not 0, then f is not in the ideal. So this is the algorithm for solving the membership problem. This problem is called the membership problem because we want to check if an element f is a member of this subset, or the member of the ideal. So that's why it's called the membership problem. And here is the solution. If you take an arbitrary Grabner basis of I, then the element f belongs to I if and only if its remainder with respect to this Grabner basis is 0. This is how to solve this membership problem. Okay. Yep. So this is the first. So this is the algorithm for the first problem. And just in case, I just want to give you some remark regarding this algorithm. Well, this part actually doesn't require G to be the Grabner basis, but this part does. Indeed, if you have a polynomial and you can reduce it to 0 with respect to G, what does it mean exactly? It means that, well, you have a sequence of elementary reductions such that at the end you will get 0. But what does it mean? Well, what is F1? F1 is by definition F minus, well, some term like coefficient with monomial C1, M1, G1. Just by definition, because this is the way how the elementary reduction works. Then what is F2? Is F1 minus some coefficient, some monomial, and times G2, etc. And in the end, you will get 0. So if you substitute all these formulas you'll see that at the end you can represent f in the form like this. Well, let me write it like this. The polynomials g1, g2, and gk could be the same, but in general you can represent them as this, and plus the zero remainder. So this is the remainder. So if you can reduce your polynomial to a zero, then it's definitely inside the ideal. But in general, it's not true that, well, when the set G is not a Grabner basis, it's just an arbitrary set. It's not true that if the remainder is not zero, then your polynomial is not in the ideal. So, so the first part holds for every set, the blue part, but the red part, in this case, it's essential that G is a Grabner basis, because if G is not a Grabner basis, then it's not true. And here is an example. So if you take xy minus 1, yz minus 1, this is your ideal I, and you want to take the polynomial, and your polynomial f is x minus z. As you can see, well, if you use this set as the set G above, then you cannot reduce f with respect to this set. So f is not reducible to 0 with respect to G, where G consists of these polynomials. Because you cannot reduce, yeah, and the order is this. Yeah, I forgot to mention the order. These are the leading terms, and you cannot reduce this polynomial. So you see, the remainder is not zeroed. So f itself is a remainder with respect to this set G. But, well, as we have already calculated, we can represent this polynomial in this form. So just by definition, it belongs to the ideal I. So because this is your G1, this is your G2. So x minus z is represented as a linear combination of these polynomials with polynomial coefficients. So it's inside the ideal, but the remainder is not zero. And the reason why this test doesn't work, because G is not a Grabner basis. And this polynomial is actually the S polynomial of these two generators. So here, G is not a Grabner basis. So it's important to use the Grabner basis in this test. Okay, that was the solution for the first problem. Again, I do not prove why this works. I just want to explain the algorithms, and I want to postpone all the details to the next lecture, because I want to give somehow an overview of the of everything we can do with the Grabner basis. Because somehow proof is the worst thing that we have in math, because somehow you cannot see the theory through the through all the proofs. Yeah. So yeah, let's. So now I want to discuss the other problem. The problem number 2. Here, what I want to do is this. So suppose I have a polynomial ring, and I want to divide, yeah, F is a field, as always. So I have a polynomial ring, and I want to divide the variables into subsets. And suppose I'm given an ideal, and this ideal is also given by the polynomial G1, K here should be different, Jm, is given by the polynomials from this ring. Now, what I want to solve, I want to find the intersection of this ideal with the polynomial ring in variables x1, xk. So I want to find all the polynomials inside the ideal I depending on x1, xk only. Well, this problem actually is very important for because of several reasons. I won't have enough time to explain why this problem is important, but one of the examples, you can compute intersection of ideals using this problem, and you can solve a lot of geometric problems using this thing. You can you can find implicit. You can find. Let's formulate it like this. So if you have a parametrized surface, you can find equations for this parametrized surface, or you can find some singular points on curves or surfaces, and so on and so on. There are a lot of algorithms based on this task. So it's just a very important building block. So if you know how to intersect an ideal with a polynomial in a smaller amount of variables, we can apply it in many places. So let me explain how do we solve this problem. As usual, first of all, we need to specify an order. But here we need to specify a very specific one. So I want to choose a lexicographical order, but in such a way that the variables x1, xk are strictly smaller than the variables xk plus 1, xn. So the order here doesn't matter. So here you may use any order. And here you may use any order. So any lexicographical order where x1, xk are strictly smaller than xk plus 1, xn is an appropriate one. So for example, you may take just the order where x1 is smaller than x2, and it's smaller than, etc., than xk, and so on and so on. Okay, then what you should do is this. The second part, sorry, wrong color. You take this, your ideal I, generated by G1, Gm, and you compute the Grabner basis with respect to this order. Then this Grabner basis, well, it consists of polynomials in all, well, probably in all the variables x1, xn. What you do, the step number 3, you define G0 as the set of all polynomials G from G capital, such that G depends on x1, xk. So you just take from this set all the polynomials depending on x1, xk only. And the claim is that G0 generates the intersection. So the claim is that this intersection is generated by G0. Moreover, you can tell more what actually happens here. Well, as you remember, we have already fixed an order for all the variables. In particular, here we have some order, let me call it lex prime. So this is the order for the first k variables. So here we have this order lex prime. So what is true is that G0 is a Grabner basis with respect to this order of this intersection. This intersection will be an ideal inside the polynomial ring in variables x1, xk. And this set G0 we have constructed here is actually a Grabner basis of this ideal with respect to this part of the order. So yeah, so these are two problems that we can solve using Grabner basis. Just in case, I want to clarify that what is important currently is to understand the steps you need to do in order to solve the problem. It's not very important to understand why the steps work. we will explain this during the next lecture. But it's very important to understand what you should do in order to solve the problem. That's the first part. The second part is why it works. Well, it's just an orthogonal question, but we will discuss this question later. And yeah, by the way, this is everything that I wanted to tell you today. Just in case, are there any questions regarding the lecture?
Well, I have a lot of questions.
But before you start, probably some other guys have questions, guys, just in case. I will answer, Kirill, to your questions, no problem, but probably some others have the questions. Okay, well, guys, then if there are no questions, then thanks for being here. As usual, I will share the lecture notes. You will find everything there. Yeah, and yeah, Kirill, now, yeah, please ask your questions.
Okay, the most important question, when we're going to have a final test?
Okay, yeah, well, I wanted to make the test this Saturday, but the Saturday is the holiday, so I have to find a new day. So during the next week, we will organize the test.
During the week or weekends?
I believe during the week. Is it important or not?
Yeah, I will tell you later. Okay, according to, back to the question, to the lecture, I didn't get 2 points. What is the set of reminders? Why do we need to multiply something?
Oh, again, yeah, let me show you.
It was in the second column in the bottom.
The second column in the bottom. Oh, okay, yeah. So again, when you have a set of polynomials, here it's G0. You have this reduction procedure. So you can take an arbitrary polynomial f and you can reduce this polynomial f with respect to G0 to something, and this something cannot be reduced any further. And if you get a polynomial which cannot be reduced, it's called a remainder.
Okay.
This is just by definition. It's something that you cannot reduce. And explicitly, how do you check if a polynomial is reducible or not? You see, well, how does reduction work? You take your polynomial, you should find a monomial inside this polynomial,
Yeah,
such that this monomial is divisible by a leading monomial of something from here.
Yep.
If every monomial here is not divisible by a leading monomial from here, then it's a remainder.
Okay.
So basically what you should do, you write down all the monomials, I mean, figuratively, not literally, but just take all the monomials. Then every monomial is either divisible by a leading term from here or not divisible.
Okay.
Take all the monomials that are not divisible by the leading monomials of polynomials from here. These monomials generate this set of remainders. Their linear combinations with coefficients from the field are all remainders.
Well, yeah, okay, it's clear, but why do we need f plus f prime and f by f prime?
Why do we need the addition and multiplication?
Yeah, just because it's a field and they're there?
Because I want this to be a ring. Because if it's, well, currently this line defines this guy as a set. So it's just a set of remainders. It's not an interesting object.
Okay, and we want a ring. That's why we have all combinations like with pluses and multiplication, right?
Yep. Exactly.
Okay. Okay, another question. You said take all polynomials f such that there is no such a monomial. And what if we take another one which is reducible, and in the end we will get a new remainder? Is it possible?
Again?
You said let's take all polynomials from such a field. then
Ring.
take
Ring.
all reducible polynomials. What if I take a reducible polynomial and find a new remainder, completely new remainder that you don't have?
But by definition, remainder, if you take a reducible polynomial and you compute its remainder, it's a remainder, so it must belong to that set.
Yeah, I mean, is it possible to find a new remainder after reduction? You have a set of polynomials, and some of them they're already remainders. Is it possible to take a reducible polynomial and find a completely new remainder?
No, well, since it's a remainder, it will be listed in the list of remainders. I don't get the. I believe I should. Well, you see. Well, let's say it's. Well, let me give you the following example. Let's take polynomials in one variable. Okay.
Okay.
Let's take polynomial something like x squared. Let's say x cubed. Then all the monomials are just powers of x. You have monomials divisible by x cubed. These are monomials. These are powers of x of degree 3 and larger. And you have monomials that are not divisible by the powers by x cubed. These are 1x and x squared. Okay. So then, if you have a polynomial which is well, if you have a remainder, what does it mean that you have a remainder with respect to x cubed? It means that you have a polynomial such that all its monomials are not divisible by x cubed. Then it's automatically a linear combination of 1x and x squared. So these guys give you all possible remainders.
Yeah, okay. I mean, okay, what does this notation mean? F bracket XXX bracket.
F bracket x1, etc., xn bracket.
Yeah, it's a field of all polynomials, right?
It's the ring of all polynomials. It's not a field. You cannot divide by polynomials here. It consists of all polynomials, and this is a ring. Yeah.
Okay, my question was a little bit different. Imagine we have such a field, such a ring. And somewhere within this ring, we have a set of remainders, right?
With respect to
G0.
Okay.
Okay, and we have another set of reducible polynomials, right?
So let me write this down because it's hard to follow. So I will clear this after your question. So we have the set of all polynomials.
Yeah, we have a ring.
Yeah, we have this ring. And we fix the order and we fix a set G0. Let's say a Grabner basis with respect to x. Yeah.
Yes.
Then for each polynomial, it's true. If you take an arbitrary polynomial here, f, it's true that either you can reduce, let's say, or the second claim.
It's a remainder.
Yeah, it's a remainder.
Okay. Is it possible that f prime isn't equal to some remainder?
Well, if you make one elementary reduction and it remains reducible, then it's not a remainder. But if you repeat this process several times,
yeah, and finally get the remainder, is it an element of the ring?
Of which one? Of the ring of remainders?
F,
yeah,
initial. By definition of the ring? Yeah.
Yeah. I mean, it's a polynomial, so it's an element of this ring.
Okay,
and
in the ring
also,
we have all polynomials.
In this ring you have all polynomials, but in this ring we have only remainders.
Yeah, I'm just forgot the not the definition, but the theology of the ring. I mean, if I found the remainder of if I found a remainder, okay, if I had f as a polynomial and successfully find his remainder, is it an element of my ring as well?
Again, if you have a polynomial f from here and you take its remainder with respect to G0, then is this R prime an element of what? Of this ring?
Yes.
Polynomials?
Yes.
Of course, because all the operations are inside these polynomial rings.
Okay.
And everything that you produce and at each step is a polynomial in several variables with coefficients in F. So
Okay.
it's not an issue.
Okay. And okay, it's clear. Thank you.
Okay, no problem.
And you also said that Grabner basis is not unique.
Yep, Grabner basis is not unique.
And you gave an algorithm how to find this Grabner basis.
Well, I gave you an algorithm to find at least one Grabner basis.
So we know the way how to find only one. If I want to find two of them, I'm lost.
Well, first of all, there are infinitely many Grabner bases. And the reason for this is the following. If you are given a Grabner basis, and if you add any amount of polynomials to a Grabner basis, it remains a Grabner basis. So if you extend a Grabner, but in the following sense, so again, if you have a Grabner basis and you add a polynomial from the ideal generated by the Grabner basis to the set, it still remains a Grabner basis. So somehow there are infinitely many Grabner bases. So just let me write this down just in case. So if you have an ideal in this polynomial ring, and suppose G here is a Grabner basis for I. So it simply means that it's a Grabner basis and it generates I. So I is generated by G. So then if you take an arbitrary set of polynomials, let's use a different letter, H from I inside I, then G union H is also a Grabner basis for I. So if you, this explains that you have like infinitely many Grabner bases. So it's impossible to find. No, well, somehow it's possible to describe all the Grabner bases, but it doesn't make sense to find all the Grabner bases. But there is somehow a canonical Grabner basis. If you fix an order, for each order there is what's called minimal auto-reduced Grabner basis. And this guy is unique.
Okay.
I don't know. We will probably discuss this during the next seminar, but not during this one.
Okay. Could you stop the record?
Okay, no problem.